Okay, now we're going to look at chemical properties of halogenoalkanes. All right. So let's again look at the example of chloroethane. Okay, so here I have chloroethane. Okay, it's a halogenoalkane, or it's a chloroalkane. All right, and what we've already seen is that we have a dipole over here. Okay, we have a partial positive on the carbon atom and we have a partial negative on the chlorine atom. So firstly, what we notice over here is that we have a saturated compound, especially if you look at the carbon atom. If you look at the carbon atom that has the functional group, the carbon atom with the chlorine, okay, this is a saturated carbon atom. It's a saturated, right? Saturated compound. Okay, and you have a saturated carbon atom here. So then, will this be able to undergo addition reactions like alkenes? No. So then what type of reactions will it undergo? Substitution reactions, right? You can't really add more things because these carbon atoms can bond to 4 things and they're already bonded to 4 things. So in order to make this guy react, if you want to react with something, in a reaction something can substitute for the chlorine atom. So they undergo substitution reactions. Okay, that's the first idea. They undergo substitution reactions because they're saturated. All right, so we have a substitution reaction taking place. Okay, that's the first thing. And the second idea is if you look at the carbon atom, it has a partial positive charge. Okay, it has a partial positive charge, and this carbon atom here is set to attract nucleophiles. Okay, it's set to attract nucleophiles. So it attracts nucleophiles. So what exactly are nucleophiles? So over here what we have is a nucleophile. Okay, a nucleophile is a species that donates a pair of electrons. It donates a pair of electrons, okay, to form a dative bond with another species. Okay, and they usually have a you can just say they have a partial negative or a negative charge. So because this delta positive carbon, right, the carbon atom which has the functional group on it is partially positive, it attracts nucleophiles, and because it's a saturated compound, it undergoes substitution reactions. Hence we say that the name of the mechanism is nucleophilic substitution. Okay, this is the name of the mechanism. So the first nucleophilic substitution reaction that we're going to look at is this one. Let's say that I have something like chloroethane, okay, and what I do is I react this with NaOH aqueous. Okay, I react this with NaOH aqueous and I heat under reflux. I already explained to you guys what heat under reflux is, right? So if I heat under reflux with NaOH aqueous, I end up making an alcohol and sodium chloride. Okay, so what I'm doing is I'm substituting hydroxide for chloride over here. Okay, so this is the nucleophilic substitution reaction. All right. Now, before we go into the nucleophilic substitution mechanism, I want to make a few distinctions here. Okay. First, let's try to distinguish between the 3 different types of halogenoalkanes that we're going to look at. We have primary halogenoalkanes. Primary halogenoalkanes में क्या होता है? An example of a primary halogenoalkane is this guy. Okay. This is a primary halogenoalkane because the carbon that's bonded to the chlorine, is bonded to just one other carbon. The carbon bonded to the chlorine is just bonded to one other carbon. Okay. So it's a primary halogenoalkane because the carbon bonded to the chlorine is bonded to two hydrogen atoms and one carbon atom. Okay, when we talk about secondary halogenoalkanes, Okay, secondary halogenoalkanes. What do you have? You have something like this. This is an example of a secondary halogenoalkane. Why is this a secondary halogenoalkane? Because the carbon that's bonded to the chlorine is bonded to just one hydrogen atom. Okay, so in a primary halogenoalkane, what you have is something like this. You have a CH2X. In other words, X over here represents the halogen atom. So the halogen atom is bonded to a carbon that's bonded to two hydrogens and just one carbon atom. In a secondary halogenoalkane, the carbon atom is bonded to just one hydrogen atom and two carbon atoms. The word primary means bonded to one carbon atom. The word secondary means that the carbon with the halogen is bonded to two carbon atoms. So over here you have something like a CHX group. Okay, you have two carbon atoms bonded to this carbon. And then obviously the last type of halogen that we're going to look at, halogenoalkane we're going to look at is tertiary halogenoalkanes. Okay. Tertiary halogenoalkanes में क्या होता है? The carbon that has the halogen is bonded to three carbon atoms. We can clearly see that here. This carbon atom has no hydrogen atoms bonded to it and is bonded to three carbon atoms, hence it's called a tertiary halogenoalkane. Okay. And primary halogenoalkanes are also known as 1-degree halogenoalkanes, secondary can be called 2-degree halogenoalkanes, and tertiary can be called 3-degree halogenoalkanes. And this obviously number represents the number of carbon atoms that the carbon bonded to the halogen is bonded to. Okay. All right. So now, when we talk about nucleophilic substitution, okay, there are two types of nucleophilic substitution mechanisms. The first type is called the SN1 mechanism, and the other type of mechanism is called the SN2 mechanism. Okay. Over here, S stands for substitution, N stands for nucleophilic, and I'll just talk about what the 1 and 2 stand for. Okay. But you have the SN1 mechanism and the SN2 mechanism. They both come under the umbrella of nucleophilic substitution. So you have the SN1 mechanism, okay, and you have the SN2 mechanism. Okay, and when we talk about the SN1 mechanism, it's a mechanism that's favored by tertiary halogenoalkanes. Okay, it's a mechanism that's favored by tertiary halogenoalkanes, and the SN2 mechanism is favored by primary halogenoalkanes. Okay. If we talk about secondary halogenoalkanes can go through either, but generally speaking, primary halogenoalkanes pretty much always go through the SN2 mechanism, and tertiary halogenoalkanes pretty much always go through the SN1 mechanism. Okay, whereas secondary halogenoalkanes, depending on the reaction itself, can go through both. So let's start with the SN1 mechanism. Okay, again, this comes under nucleophilic substitution. So this is the SN1 nucleophilic substitution mechanism. Okay. And let's take an example. Let's say that I have this tertiary halogenoalkane. Something like this, right? Or we can just say Cl, right? This is 2-methyl or 2-chloro-2-methyl propane, right? This is the compound. 2-chloro-2-methyl propane, 3-carbon chain. So this is the compound that we have here. And if we talk about the mechanism, okay, before we talk about the mechanism, let's actually look at the reaction itself first, okay. What we have here is if we react this guy with aqueous NaOH, right, if we react this with aqueous NaOH and we heat under reflux, okay, we end up making an alcohol. Right, we end up making an alcohol. So what you're having here is you have substitution of the Cl with an OH. Right, obviously you're also making NaCl here. This is not the overall equation. This is just showing you the main organic reactant and the organic product. And now let's look at the mechanism. Now let's look at the mechanism and how it takes place. So what we have is in the first step we have over here we have a chlorine atom, right? And we have a methyl group, 1 methyl group, 2 methyl groups, and 3 methyl groups, right, on this carbon atom. This is our starting reactant. Now what happens in the first step is heterolysis of the carbon-chlorine bond. Okay, so in the first step what happens is, again, you have a delta positive carbon, you have a delta negative carbon. So in the first step of the reaction you have heterolysis of the carbon-chlorine bond. So the first step is heterolysis or heterolytic fission, right, of the CX bond. X over here represents a halogen. Okay. And again, if you remember, heterolysis kya hota hai? Both the electrons in the bond over here are going to the chlorine atom. Okay. So after heterolysis takes place, what you end up making over here is a tertiary carbocation intermediate. Right. So after heterolysis of the carbon-chlorine bond took place, right, you form Cl minus and you form this carbocation intermediate. And in the second step, what happens over here is that the hydroxide ion, which came from NaOH aqueous, now attacks this positive carbon, okay, and you end up making the final product. Which is CH3, and then you have the OH. And obviously you still have the what do you have over here? You still have that bromide ion that broke, or the chloride ion that broke off, right? So this is the SN1 mechanism. Okay, we're going to show this arrow a bit more like well defined. Okay, make sure you show it as like a curly arrow. Just making it more curly. And again, the arrow should be shown from the lone pair of electrons to the positively charged carbon atom. Alright, so the question here is, okay, this mechanism is favored by tertiary halogenoalkanes, okay, it's favored by tertiary halogenoalkanes because the tertiary carbocation intermediate is more stable than the the secondary and primary carbocation intermediate, right? So over here we're comparing tertiary and primary. Why is it favored by tertiary rather than primary? And it's because the tertiary carbocation intermediate is more stable than the primary carbocation intermediate. Okay. Due to the positive inductive effect. Yeah, in this case methyl groups, but generally just alkyl groups. Okay, positive inductive effect of the alkyl groups. Okay, alkyl groups. Okay. And again, positive induction can also be, like in simple words, it can be rephrased as the electron donating effect. Okay. So again, the mechanism, this is the SN1 mechanism. This is the SN1 mechanism, and tertiary halogenoalkanes favored because in the SN1 mechanism a carbocation is formed, and primary carbocations are highly unstable. So to form a primary carbocation, you need a very high activation energy, so it's not favored. Whereas tertiary carbocations are relatively less unstable, so you don't need as much energy to make them. So that's why tertiary halogenoalkanes prefer going through the SN1 mechanism. The SN2 mechanism, which is for primary halogenoalkanes, उसमें carbocation नहीं बनता. Okay, we're going to look at that in the next class. All right. So what I want to look at next is this guy. Okay, first I'll actually just draw the simple structure. We have this guy here. Okay. And what we have here is a tertiary halogenoalkane. What we have here is a tertiary halogenoalkane. So we have a tertiary halogenoalkane. And what I'm going to do is I'm going to react this with sodium hydroxide aqueous. And when I heat under reflux with sodium hydroxide aqueous, I end up making a tertiary alcohol. I end up making a tertiary alcohol. Okay. So I have CH, CH3 twice, and then I have OH. Right? Now what's the mechanism for this reaction? So over here, this reaction proceeds via a nucleophilic substitution reaction. This reaction, right? Nucleophilic substitution mechanism. Okay, and specifically because it's a tertiary halogenoalkane. Okay, because it's a tertiary halogenoalkane, it proceeds via a SN1 mechanism. Okay. Now again, if we drew the mechanism, and I'm going to draw the mechanism using this sort of 3D representation. I'll explain why in just a second. Okay. I'm going to put this complicated group on top because it's easier to write that way. Then you have a CH3, you have a CH3, CH2 here, and then you have the chlorine atom. Right? So what happens in the first step of this mechanism? So in the first step of this mechanism, again, make sure you show the dipoles, and what you have is you have this CCl bond breaking, right? And what you end up doing here is you end up making a carbocation intermediate, right? Now what I want everyone to appreciate over here for a second is that you were starting with an sp3 carbon, right? Tetrahedral structure, and the carbocation intermediate, if you look at this carbon, will be an sp2 carbon, right? 120-degree bond angle. So we're going from this tetrahedral carbon to a planar carbon atom. We're just looking at this carbon atom here, right? So what we end up making is this. Right? And this is your carbocation intermediate. This is your carbocation intermediate. So in the second step of this reaction, we have the hydroxide, okay? And what it does is it forms forms a dative bond with the carbocation intermediate, right? And you end up making the final product. You end up making the final product here. So the idea here is that because you have this planar carbocation intermediate, it's like a flat structure, right? So if you're looking at the screen itself, the hydroxide can either attack from the front, this carbocation, or it can attack from the back. It can either attack this carbon atom from the front or the back, and that results in a mixture of optical isomers. So what you end up doing is you end up making this. Okay. Right? This is one possible product, right? And the other possible product that you're making here is the enantiomer of this compound, right? It's the optical isomer of this compound, the non-superimposable mirror image. Right, and then you have the OH here. Okay, then you have this CH3 group, and then you have the CH2, CH3. So over here, what's happening is you started with just a single isomer. You start with a single isomer, but because this carbocation intermediate was already bonded to three different things, right, and it was a planar compound, now the hydroxide could either attack it from the front or the back, resulting in a formation of a mixture of optical isomers. So the question we can ask here is that why do we have a mixture of optical isomers forming? And the reason why is because the nucleophile, right? In this case, that's the hydroxide ion, right? Can attack the carbocation intermediate. In other words, bond to the carbocation intermediate, okay, from the front or the back, okay, resulting in a mixture of optical isomers. Right? Specifically, these types of optical isomers are called enantiomers, right? They're non-superimposable mirror images of each other. Enantiomers. Okay? So this is your mirror plane over here, obviously. So again, the question that we're asking here is why can it result, okay? Why can we have a mixture of optical isomers? Okay? Or the question may ask why is it possible to produce a mixture of optical isomers here? Okay? And the reason why is because of this. Okay? So you can write that question down. Okay? Why is a mixture of optical isomers produced? This is the question that we're answering here. So when we talk about the SN1 mechanism, right, again it's favored by tertiary carbocations or tertiary halogenoalkanes, okay, and it's a two-step mechanism, right, it's a two-step mechanism. Right? And it's the same idea. You start with the reactants here, okay, in the first step you have hydrolysis, right, and the second step you have the bond formation between the nucleophile and the carbocation. So here what you have is what do you have here? So over here you have the carbocation intermediate. In this case it's a tertiary carbocation, right? Secondary may also go through it, okay, primary pretty much never go through this mechanism. Okay? So you have your carbocation intermediate, and here you have your reactants and your products. So that's a summary of the SN1 mechanism. Okay.